There, how's everybody doing? We want to welcome back, and today we're going to talk about exponential functions as compared to linear. All right, and here we start with this first situation, which is linear. Bob will give Alice 2 pennies each day, and we want to find a function f of t that equals the number of pennies Bob gives to Alice after t days. Okay, so after 1 day, we have 2. After 2, there's 4. After 3, there's 6. And after 4, there's 8. And hopefully we recognize this function as a linear function f of t equal to 2t. All right, here, so we could, it's down in left side of my screen here in that Desmos, or your screen, f of x equal to 2x. And that's what it looks like. It's a constant rate of change of 2. Everywhere, no matter where you go, when you go from x to x plus 1, the function increases by 2. And we could see that here by, 4 minus 2 equals 2, 6 minus 4 equals 2, and 8 minus 6 equals 2. That's saying it's remaining constant no matter where we are, and that constant is the difference between the two. In some sense, I would say that linear functions are additive. Now, exponential functions, on the other hand, here's a situation that's exponential. Carl offers to double the number of pennies given to Alice each day, where on day 0 she starts with 1 penny. And we want to come up with a function. So let's see here. We start on the 0th day with 1 penny, and then next day we double that, that's 2, and the next day we double that, that's 4. Oh, it's seeming a little like it's linear, right? Oh, but wait. Now on the next day it's 8, double that 4. You see it's doubling what is there. All right, and then on the 4th day we have 16. And here, notice they change. 2 minus 1 is 1, 4 minus 2 is 2, 8 minus 4 is 4, 16 minus 8 is 8. It's not a constant slope. But what is constant here is when we divide. So 2 over 1 equals 2. 4 divided by 2 is 2. 8 divided by 4 is 4. And 16 divided by 8 is... 8 divided by 4 is 2. Excuse me. And 16 divided by 8 is 2. So here, when you divide them, and the other side of division is multiplication. So I would say that the exponential functions, they're multiplicative. And they make sense in that here, this one is increasing by 100% of what's there every day. But exponential functions in general, they're increasing by some percentage of whatever's there at that day instead of by a fixed percentage. So it matters where you are, your t values, right? T changes by 1, your function may increase. It increases by different amounts depending on where your t is. All right. So let's think about a population of bacteria growing by 10% each day, and we start with 10 bacteria. We want to try to find a function, f of t. Let's go back to this example. Linear, exponential. Let's graph this exponential, try and think of what it's going to be. Plug in some things, but here we get g of t equals 2 to the t. All right, so I'm going to plug that in my Desmos. Gx equals 2 raised to the x. Now notice here that there are times when the linear function is above the exponential, but then in the long run, the exponential really increases by a lot. And we get that little bit of curve in there. All right. And to see how much it increases, let's see. We went with Bob's deal. After 30 days, we have 60 pennies, 60 cents. Hardly worth carrying around 60 pennies in your pocket for 60 cents. However, after 30 days of Carl's deal, 1.0737 times 10 to the 9th cents. So that's 1.07 times 10 to the 7th dollars. I'd like you to think about that and why that works. Good practice with the scientific notation. Um, Quite a big difference here. And it really shows you how exponential blows up. Of course, this is an extremely large growth because it's growing by 100%. So this exponential, this is how populations work, right? If you think about a birth rate, the birth rate, it all depends on how many people are there during that year, right? There's going to be, even if you have the same birth rate, there's more babies being born when the population is 100,000 than when, with the same birth rate, when the population is only, say, 1,000, right? It'll change the actual amount, but it is changing by the same percentage of what's there. All right. So, for instance, let's think about a population of bacteria that grows by 10% each day. And here we'll start with 10 bacteria. Now let's say we want to find a function f of t that gives us the number of bacteria after t days. Well, we'll make a little chart. Notice our first 0 days we start with 10, right? Day 0 we have 10 bacteria. Then in the next day, we increase by 10%. So at the end of the first day, we have 11, right? 10 plus 10% of 10 is 11. And then what happens on the second day? Well, you have 11 there, and then you're adding, it's changing by 10% of that 11. All right, 1.1, so what is it, 12.1, so forth. Now, the way this works is this function is given by f of t equal to 10 times 1.1 to the t. And if we want to take a look at that, I'll call it h, since I already have a f in there. Okay, so notice that one, it goes through here. It goes through the 0.010. Okay, that's its initial point, 0.10. And then notice it's bigger than the higher growth rate of 100%, or actually 1 of our previous, right? But eventually that one beats it out. And notice it also starts going away from linear. We look at it over there. Okay. In general, we have f of t equals f naught, which is our initial amount, times 1 plus or minus k to the t. In our last one, our k was, in our last problem, our k was 10% or 0.1. Now, let's suppose we deposit $10,000 in an account, 3% interest compounded annually. So that works just like a population that's going by 3%, where a of t, which is the amount you have after t days, is given by 10 times 1.03 to the t. Here we call, when we're talking about money, we call that initial condition 10, or p, our principal, we call it 10. And notice I did this in thousands of dollars, so I don't have to have all the zeros. In general, for interest rate R and compounded n times per year, we have a of t equals, oh, that got moved. Let me rewrite that there. Sorry. On n times per year, we have that a of t equals our principal that we put in the bank times 1 plus the rate divided by the number of times it's compounded per year. How many times it's compounded per year, okay? So for instance, if it was compounded monthly, that n is going to be 12, all raised to the n times t, okay, which makes somewhat sense, and that's a formula we could use for money compounded n times per year. If it is compounded continuously, we use the special letter E, which is a very special number. It's you could approximate it 2.71, but it's very similar to pi, but it's on your calculators. And if it's continuous, we then have this a at t equals p times e to the rt, right? And those are our main exponential type functions. I should maybe mention that if a population is increasing continuously instead of every hour or something, it's continuously, more like a birth rate would happen, right? Then that also follows for a population, it's P of t equals our initial population, P naught, times E to the RT. Very similar there. All right. So go ahead and try some problems there in Edfinity and let me know if you have any questions. Have a great day.